My name is Zoya Gorodilova, and I'm going to tell you about the Popov-Pommerening conjecture for groups of small rank. First of all, I want to fix the field. We consider algebraically closed field with characteristic 0. Let G be a linear algebraic group. Let X be an affine algebraic variety. Hilbert's Fulton's problem asks when the algebra of invariants of action of G action on X is finitely generated.
Algebra of the field. Brackets,
It's algebra. As I know, you have discussed this problem recently, so I would stop on it and move to other questions related with this problem. If we consider a connected reductive group.
As Julian explained us, Hilbert Fulton's problem didn't ask for affine varieties. It asked about linear action on vector spaces. And this is some variation of Hilbert's Fulton.
Expression which close to the question which I want to consider for them. We consider a connected reductive group. And closed algebraic subgroup. And the question asks when the algebra of invariants of action subgroup on any variety X is finitely generated.
Only the question. Yeah.
We call subgroup H regular. If it's normalized by maximal torus in G. Popov-Pommerening independently conjectured that if G reductive group and H a regular subgroup,
H.
H regular subgroup, then for any time
So actually, the answer is yes.
when X, this algebra is finitely generated.
But maybe to add some explanation about a regular. say, write down G is SLN. What are regular subgroup of SLN? How do they look like?
Regular subgroup of SLN, if we we can say that regular subgroups can be regular important subgroup can be parameterized to these root sets in our systems, and regular subgroups will be generated by root subgroups.
But what does it mean on the level of picture?
Seems that the torus is a regular subgroup, but it is not generated by the root subgroups.
Yeah.
But maybe in the picture it's more clear.
Yeah.
Probably it's better to write down the picture for the Lie algebras, not for groups. So for the Lie, at the Lie algebra level, you just have boxes. Each subspace is just a box. One subspace. Or maybe cell, one cell. So probably you can formulate it in terms of the root decomposition.
Yeah, I right. If we have
Just some subset.
regular will be ash.
Am I right that maybe I'm too naive, but when I consider a regular subgroup in GLN, then just every element is almost independent on another ones, and so either this element is non-zero or this element is anything or just zero, something like this.
Just write down, you started with unipotent subgroup. Write down the matrix. So if it is unipotent, then you have units on the diagonal, zeros downstairs, and some stars upstairs. No, put several stars. Not everywhere, somewhere zero, somewhere stars. Okay, so draw some pictures, some zeros and some stars. Certainly it should be a subgroup, so this location of stars should be not arbitrary, otherwise it will be not a subgroup. But if it is a subgroup, the condition that it is regular means, as Sergei said, that stars are arbitrary numbers, and at some locations you have zeros, right?
Yes.
So this is a condition to be regular. Okay, but these are unipotent regular. And can you give us example of a reductive regular subgroup in SLN? Dear colleagues, please help us.
Torus.
A torus, the SLN minus 1, I think.
Torus is okay. What else? What is SLN minus 1? How should we subtract 1 from SLN? Who said SLN minus 1?
That's me.
What do you mean?
I mean that in the angle, in the left upper angle.
Can you draw the corresponding picture?
Centralizers of singular torus.
No, on another plate, here somewhere, not overlapping to subgroup, but to draw a separate picture for this subgroup.
At the bottom also.
Do you mean this?
But SLN minus 1 on the diagonal, not units, but just big star. And zeros, yes. And here, well, okay, something like this.
So these stars this time this is not the same as in the unipotent case because they are not arbitrary. But the only condition is that this angle, all the stars, they form either non-degenerate matrix or matrix with determinant 1. But this is only the condition on the stars. Modulo this, they are arbitrary. Okay? So this is exactly the condition. The corresponding Lie algebra is a linear sum of some root subspaces. Okay. So if we fix the suddenly this is all for fixed maximal torus, for the maximal torus of all diagonal matrices. Then the regular subgroup are given by some combinatorial data. When you fix those root subgroups, which generate our algebra, but as a linear space, so not as a Lie algebra, but as a linear space. Okay.
For first discussion, we need to fix some notation. In our G, we fix the subgroup. And in this group, we fix maximal torus. And maximal invariants group. And also we need to fix root system of G with respect to fixed torus. Fix set of positive roots. Fix simple roots.
And here G is what? It's just
G
linear
is-
algebraic group
Connected
connected to
reductive. To consider this conjecture, we can impose some reductions on group G and its group H. First of all, we can consider a transfer principle. It tells that if we have a German, then we have the following isomorphism. And if we apply this principle to algebra, we get that to find the algebra of invariants, to check is it finitely generated. It is suffice to consider this algebra. If algebra on homogeneous space will be finitely generated, then we get that this algebra will be finitely generated too.
So write down. This implies such an arrow that if for any x,
I'm sorry, it's clear, but why tensor product is finitely generated if both multiples? So it's not clear for me this arrow.
G is reductive.
Is it obvious?
G is reductive, and if both algebras is finitely
Okay.
generated.
Sir Alexandrovich, control question. If both algebras are finitely generated, why their tensor product is also finitely generated?
I think you can just take off the generators of both parts.
And consider their product?
Something like this.
No. Bad idea. Who can say?
Take product with one.
Oh, yes.
Take first generators with one and then one with second generator. Okay.
But here the question is not this. Here you have G, but okay, if G is
Reductive,
then
then this implies finite generation. So we don't need to consider all affine varieties. We need to consider only one variety.
Yeah,
This is not necessarily affine, but this homogeneous spaces is always quasi-projective, so we should consider this.
Yeah, we can restrict our consideration only on pair G and H.
G mod H.
Also, we can say that it's suffice to consider H unipotent. If we take any algebraic group and consider its unipotent vertical. Then motion group will be reductive. And the algebra of invariants in written it means that if this algebra is finitely generated, and because of this is reductive, we get that this algebra will be finitely generated. So we can say that we assume that H is unipotent group in our earlier fixed maximal unipotent group U, and it's normalized by our fixed torus.
But some comments are, firstly, this transfer of principle, this is not obvious statement. This is some claim. This is, I don't remember whether it's proved in Popov-Pommerening book, but maybe it's proved. So this is some non-trivial statement, but
Exactly.
to prove this isomorphism, this between left and the right side in this, you need some arguments. This is not immediate, but this is true. Okay, so we believe in this. Second, please write down that this KGH, like this. Yes, this is equal to the algebra of regular function on the homogeneous space. This is more or less the definition of the algebra of regular function on the homogeneous space. Again, you need to think about this, because this homogeneous space is maybe quasi-projective in general. maybe non-affine, non-projective. But if you will analyze the structure of algebraic variety here, you will see that algebra of regular functions here is algebra of invariants. Okay.
And H is contained in U because of Sukhanov
No,
criteria?
just because this is a unipotent subgroup, and a unipotent subgroup is conjugate to subgroup and maximal.
We can consider subgroups up to conjugation.
Okay.
Sukhanov criterion is only for quasi-affine homogeneous spaces.
But you said something about quasi-affine.
No, this is for arbitrary range.
With this restriction, we can reformulate the conjecture and tell that for any regular unipotent subgroup, algebra of invariant must be finitely generated. The other reduction we can consider is if we suppose that there exists such connected reductive subgroup.
It's not clear for me. When we, I'm sorry to interrupt, but when we conjugate H, it can become non-regular because you conjugate the torus, and it's unclear for me at all.
No, or just take this unipotent radical. This is normalized by the maximal torus.
Yes.
So you may consider the semi-direct product of this torus and this H.
Okay.
This is a solvable subgroup, connected solvable.
And
And by Borel's theorem, this is conjugate to upper triangular matrix, and inside of this Borel subgroup, any unipotent is conjugate to...
Okay, thank you.
No, it's, what I said at the end, it's not needed. This will automatically in the unipotent.
If we consider such inclusions, we get that if this algebra is finitely generated, then this algebra generated, it follows from the transform principle if we take V as algebra as regular functions on the group G. Also, we can say that it suffices to consider when J is simple and simply connected. And now I want to formulate some known results about this conjecture. It has been proven for groups with type less or equals 4 B2 and G2 by unit time. Groskans proved that if H important radical of parabolic subgroup, and then for such pair G and H, the conjecture is true. To formulate the next result, I need to...
But let us discuss a bit.
Yeah.
Please draw SL4. So prepare such a picture for matrices 4 by 4. Draw with such a picture with stars unipotent radical of some parabolic subgroup.
We can say that if we consider the algebra of this parabolic subgroup, it will be torus with some subspace. We need to take some subset in our simple roots, and then the algebra of parabolic subgroup will be
Well, I think this is it to just draw this. But okay.
Okay, this you can do deep inside. We want just pictures. What are unipotent radicals of parabolic subgroups?
it will be corresponds to this algebra and
Just an example.
Block upper triangle.
it's upper triangle, and then we need to
Conceptologist. Block.
This is unipotent radical of some parabolic subgroup.
no.
So you remove the levy part.
Yes, so this is an example.
Okay, this is first example. One more example. Let us draw all of them up to conjugation. No. Produce another picture. We will produce another picture.
So there are lots of them.
Okay, but we will just up to conjugation. Okay.
And also an automorphism.
Automorphism, right? Also transponent transposition.
Position. No, but
With respect to the anti-diagonal.
No.
The first mistake.
so that right upper should be star. Yes.
So they are encoded by a subset of the set of simple roots, right?
Yeah.
So how many simple roots do you have?
Sorry.
3. How many subsets do you have?
Eight.
8. But we don't consider symmetric subspace, okay?
Yeah.
So please list all subset of the set of 3 elements up to such symmetry. No, just a combinatorial question. List all subsets. Okay, first one. Okay. No, simple roots. Simple roots. Okay. and more.
No, this is symmetric to alpha 1, alpha 2. Just alpha 2 is interesting.
Yeah.
Okay.
And
But
empty set.
empty set also. So which picture corresponds? Enumerate them. 1, 2, 3, 4. Okay. So which correspond to what?
This is 3.
Okay. And give us an example of a regular unipotent subgroup here in SL4, which is not unipotent radical of some parabolic subgroup. So Groskans gave a positive answer in the case of 1, 2, 3, and so on, because they are unipotent radicals of parabolic subgroups.
When we consider regular unipotent subgroups in reductive groups, we can say that they correspond to root subsets into in our root system. It means that every regular important subgroup can be parameterized, but by some subset in set of positive roots that closed under addition. It means that sum of any roots in this set is either belong to it or is not a root at all. And such regular important subgroups will be generated by root subgroups our set phi. We already considered this. We can consider this as an example of root subgroup. And for this phi corresponds this unipotent subgroups regular. Knopf proved that if
No. Knorr, this is some company which produced some artificial eating, but Friedrich Knopf with 1p.
he proved that if the complement to the set phi in the positive roots is linearly independent or there is a unique linear dependence, then the conjecture is to we can write it as rank of this set is greater or equal the amount elements of each minus 1. For example, according to his results,
In this case, the conjecture is true.
yes,
So we assume that this complement is linearly independent.
it's if it's linearly independent or there is a unique linear dependence in this set, then the conjecture is true.
And this
This
This condition exactly means this. So if rank is equal to number of elements, then they are independent, and if minus one, then you have only one relation between them.
And the last result was about conjecture was obtained by Verci in 2018. He proved it for some special cells. In types. His conjecture that H might be normalized B and there is some special rules in it. A standard approach to check this conjecture is the Grossman's criteria. It tells that if Gaussian loop the following conditions are equivalent. The algebra of invariance is finitely generated. Is equal to there exists such finite dimension geometry and vector image that H is a stabilizer of this vector and dimension of the boundary of the orbit is greater or equal to Linton and Verci used this criteria to get the results. And now I want to consider other approach for testing the conjecture. First of all, I want to use that the final generation of this algebra is equivalent to final generation of this algebra where U minus is the opposite maximum subgroup to U, maximum important subgroup to U, and U minus us on G on the left and H on the right.
Is finitely generated.
And we're going to consider this algebra. We adapted a method that was firstly used by Kucherenko, who solved the similar problem connected with the branching problem. We want consider the big cell in G.
Here H is a subgroup of U?
H is subgroup of maximum important, and we consider opposite to U, and take this algebra of invariance. have an inclusion of algebra.
But this direct product invariance with respect to the direct product is invariance with respect to group generated by them, yes? And so
No, this is indeed a direct product. Or not?
this they generate a parabolic group. Am I right?
No. One of them acts on the left and the other one on the right.
Ah.
So this is not a product of this subgroup inside of group G, but this is a direct product acting on both sides.
Okay, I'm sorry.
This inclusion and this algebra can be easily found. Because of who minus acts on the left and H acts on the right, we can write in the following way, and this will be the product of algebra. The rank of a group, and K is the amount of roots in the complement. Then we can fix for all input to each regular function that we extend to regular function on the whole algebra. And then regular functions on torus will be following, and have that.
So these are basis characters.
Yeah. And our importance group can be represented as the product of root subgroups, where root subgroups are taken in any order, and we can fix such order on each. First roots form the complement. And others belongs to V. Then we get that this portion group will be the product of these first K root subgroups, and we can fix a coordinate on each of these groups. And get this algebra by these coordinates.
You mean the variety U mod H is isomorphic to
Yeah,
this?
So what you are doing now?
Now I find this algebra invariance, and I want to say that this algebra will consist from all functions from this algebra that extends regularly to the whole group. We know how this algebra looks, and now we want to find which functions will be regularly extended to
So you explain us some technique how to prove this conjecture in particular cases.
Yeah, I want to explain algorithm that let us to find this algebra.
Compute explicitly.
To compute the generators of this algebra.
Okay, but let me understand the logic. So you listed some known result. You are finished with this.
Yes.
So this is all known result on this subject.
Not all. There are some more, but
Those which you wanted to mention.
yes.
Okay? Now, what is your global aim up to the end of the seminar? You want to prove some positive results?
No, I want to tell about some new approach that let us get some really positive results.
Do you going to report on your own results
Yes.
within this technique?
Yes.
Okay, clear.
As I said, we want to extend, to understand which functions from this algebra can be extended regularly to our group. To do this, we consider the relative composition of our group.
Actually, and this criterion is not straightforward. Yes, it's some theorem or it's something obviously. Yes, it's obvious or it's some from left to right. I think it's obvious.
Yes.
So this is Hadji's theory.
Yes.
From left to right or both directions.
It's
More
suggests from
complicated direction. So from left to the right.
From the left to it's
then we can transpose our group to the Bura cells. The big cell corresponds to the case when we take omega is factorial, and if we consider simple reflections, these Bura cells gives us the open sets of dimension 1. And its closure will be prime divisors. This will be the only cells with dimension 1, and if we consider the complement of this big cell in the whole group, it can be written as the union of these prime divisors, and then it can be represented as the union of these open sets with other components with dimension greater or equal to. We can consider a new set, from which we exclude all the dividers except one fixed. Then we have conclusions of algebra. to check if some functions from the big cell can be extended to the whole group. It's sufficient to check that it's a regular order every open cell.
And just seems rather obvious that function is regular if it's regular in something with boundary of codimension 2.
Yeah, yeah.
So, but it's worth mentioning that each subset omega I is obtained from the big cell by just gluing one divisor. Omega, not G, but omega.
And to check what functions will be regular on every such open set, we need to find the orders of our coordinate functions along these divisors. It's some technical calculation, so I just claim that if we take coordinate on torus, then order of torus coordinate on the divisors the I is equal the coordinate data, and to calculate the orders of coordinate fractions in a Bolton group, we can consider the revised subgroup generated by torus and some root subgroups corresponding to a simple group.
So this is a minimal level subgroup.
Yeah. And as I already mentioned, we can take any numbering on the root system to get the maximal importance of the group, and if we renumber it any in such a way that first coordinate will be corresponds to the single root, to the fixed single root. Then we provide other coordinates on our group. Orders of these coordinates along our fixed devices will be equal -1 if I equal G and 0 otherwise. When we consider different coordinates, we can get some coordinate changes, and if we write the equation where we can express our first fixed coordinates with using our new coordinates as some polynomial equation, and then orders of our coordinates will be equal the degree of this polynomial according to the first coordinate. And when we know all orders of the coordinate functions, we can define a new function which will be such, which will be multiplied to such powers, but by minimum possible degree. So that this function has no pole along any divisor. So it will be a regular function on the whole loop. And we can rewrite the algebra on the big cell using this new function. To consider some new algebras. If we this algebra, it has no poles at all, and
so actually the problem is to find all functions in this algebra which are regular on the whole G.
yes.
So we have this algebra.
Yeah, we want to know, we want to understand which functions will be regularly extended to the whole group. We want to start from this algebra, and it's subalgebra in our group, in algebra that we are interested. And we want to consider a
The
chain.
illusion is it in the other direction?
No. It's called regular functions.
Regular function, okay.
We want sequentially add negative degrees of
Negative powers.
negative powers of coordinate of torus to our algebra and check which factors will be regular on OG. And this gives us chain conclusions. The last algebra will be equal to the algebra which we want to find. So we want to calculate every this algebra to get the last one. To do this, we consider some new algebras. If we
So we start with A0, and we
Yes.
want to subsequently
It gets-
compute all these algebras
yes,
in this increasing chain.
And if it's finite, if on the final step it's not finitely generated, then it will be, will become not finitely generated at some step.
yes. And if we at each step we get the finite generated algebra, then we get that for this h the conjecture is true. To calculate these algebras, we consider construct the following algebras and take regular functions on our open sets such that these functions multiplied by some power of torus coordinate belong to our previous algebra. And then we again get chain.
AI0 is just AI, right?
Yes. It means that we sequentially add negative degrees of torus coordinate on each step and check which functions will be regular. If we
So this is an infinite series, right? It's an
yes.
infinite chain of inclusions.
and in
And
each
its union
the union of this inclusion will be equal to the
next algebra.
next algebra.
This is not an algebra. Aij, is it an algebra?
Yes.
It's because our condition, if two elements are sent into algebra after multiplying by something, then their product is sent to, should be multiplied by the square of this element to get it. I think that this is Aij squared. Elements lie in Ai2j. Maybe I don't know. So the whole I plus 1 is algebra, but Aij is not. I don't understand.
I don't catch what is the problem.
So the problem is that if you have two functions with this condition that's multiplied by something that belong to AI, then their product should be multiplied by the square of this something to belong to AI. So
This is not subalgebras, yes? Aij.
This is my
Are they
Just
algebras?
subspaces. But their union is an algebra.
Yes, okay. Thank you.
Something like the gradient.
Yeah.
Filtrate.
No, filtrate.
And now we want to sequentially construct these algebras. To do this,
We decided that they are not algebras.
oh, to this subsets. Subspaces. We want to consider such a deal, and consider the subspace. And if we get that this will be this will be ideal that generated by some function, then we get that the subspace is we can write it. We get that
Sorry, but I don't understand that. We decided that Aij is not subalgebra,
Yeah.
but you write that Aij plus 1 is generated as an algebra by something over Aij.
Actually,
What
it
is
should be an algebra. So probably we just should modify the definition.
if we
Seems that you add not f, but maybe f divided by something to obtain algebra.
Okay, we have 10 minutes, and talk should be useful, so people should learn something from what you say. So what people do learn now?
now it's some technical.
Okay, what is the aim? So what is the final result?
Final result, if we get that if this sequence stabilizes, then we get that for this chain, then we while getting these algebras at each step we edit the finite set of generators, and if at each step our algebra is finitely generated, in these steps, we calculate this algebra.
Okay, this is the idea of the proof, but
Yeah.
does it work? So does the sequence terminate, or so what is the result?
Yes, we deal to prove using this algorithm the conjecture for the groups of type B3 and C3. And from these results, we get that the conjecture is true for all groups with rank less or equal to 3.
This is complementary to Linton result.
Yes, he proved he.
Because it was some scandal with this Linton, but I will tell you later, okay?
He proved for some small groups and for A3, and we get for B3 and C3 using this algorithm.
So using this technique, you
Yes.
consider all regular unipotent subgroups in groups of type B3 and C3 and prove that the algebra of invariants is finitely generated.
Yes.
And how do you do this? You consider just case by case all regular unipotent subgroups?
For some regular unipotent subgroups, the conjecture is true from previously known results, and I can say that there are in B3 and C3 there are 122 feet that are closed under addition and have rank 3. Because we can consider subgroups after conjugate, it left only 35 subgroups in B3 and 32 in C3, and using the known results, we get that we need to apply our algorithm only in 6 cases in B3 and for 7 in C3.
And this is done by you?
Yes, we implemented this algorithm in the SafeMath. It's a computer algebra system which allows to calculate the generators of the algebra.
So you can not only prove that this is finitely generated, but you can in some sense find this generator.
Yes.
And who discovered this approach?
It's which he used in the branching problem.
So this is a PhD student of Dmitry Timashov?
Some guy in Moscow State University
Yes.
Found this approach.
Yes.
And you learn from him.
Yes.
Does he have some paper on this?
He has preprint.
Has submitted a paper.
Yeah.
And what he did?
He did branching algebra for
F4.
using this algorithm.
He proved Popov-Pommerening conjecture for A4, for F4.
No. So he used this approach to solve another problem, which was related to the branching from the groups of exceptional types to some reductive subgroups.
Okay.
So this is a classical problem from the representation theory.
Okay.
And his result was related to a case where actually he computed this very algebra for some concrete case where G is of type F4 and H is just a maximal unipotent subgroup of B4.
And who realized that this can be applied to Popov-Pommerening conjecture? Sorry? Timashov proposed you to study this problem, and you did. But what to publish if it is done by computer? So
It's okay.
So the algorithm.
Computer science is something.
You take computer author.
and go further, this will be more and more complicated.
If Sergey, is it the same algorithm that was described by Van Essen for finding generated?
Seems that no, it's have the same form, but the algorithm is another. I think.
It looks somehow similar.
Yeah, it's just somehow similar, but I can't say that this is the same algorithm. And what is the, maybe, I don't know, the most interesting open question in this field? So what particular case is interesting now?
To consider it for higher ranks, but
Before is known or not. So, can you just say that, okay, A bigger than 4 is known, yes?
No,
Not bigger.
no.
Okay.
So in type A, the largest known example is 4.
It's 4.
A4.
Smaller than 4 is, okay, A4. A5 is open. B4 is known, B4 is open.
before that.
So, okay. And are there some papers which some condition on H, I don't know, H's. Okay, there was, for example, H's which are unipotent radical of parabolic groups, but maybe some other particular cases.
Bike no, if you remember.
Is condition to the
This linear independent or almost linear independent.
and
But it's rather strange condition, or maybe.
No, it's a natural condition because the complement is small in some sense.
and the previous result obtained by Berchi, who proved the conjecture for special condition on subset of
So I guess to hear that there is this group and this subgroup, and nobody knows whether the homogeneous space have finitely generated algebra. Is this? Do you have such a pair with open question that nobody knows, or just?
No, but to do the same calculation for rank 4, take all possible configuration, exclude those which are covered by.
Okay, but it's boring. I thought that there is a couple which is some special couple. I don't know. Okay.
As to me, I would propose, say, consider one-dimensional regular subgroup. Then I think that the answer is yes. This should be clear. But take two commuting unipotent subgroups, two commuting root subgroups. For them, I think the conjecture is open, and this is an interesting particular case.
Sasha, maybe you're right, because each root subgroup is somehow local nilpotent derivation, and invariants are just kernel of local nilpotent derivation, and maybe this is the same algorithm.
Well, maybe that in the when the algorithm there are two parts. First part goes for kernels, the second part just for localization. The part for localization is exactly this.
It's just that I believe that now I believe that it is the same.
Okay, so you are done?
Yes.
Any more questions? If not, then thanks to Zoya, Shaparevich will recall our hands. So, camera raise.